Hey everybody, this is Larry. This is me going Q4 of the bi-weekly contest 134, shortest path in a rated tree. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this one. So this one I will start by drawing, so give me a second to set up this. Should have had this set up, but well, technology, you know. But the first thing notice for this problem is that that my table is kind of dirty. But the second thing after that is that it is a tree, right? And what does it mean for when we have a tree? Well, when we have a tree, a rooted them and that everything is the longest path from one node. That means that we can draw that one node in the beginning, in the top, right? And then now there's only one path from any 2 points in the tree in either case. So that means that from one there are all these you know, like whatever, right? Okay, something like that, right? So the crux of the problem is that, okay, I mean, hopefully if you're watching this video, you already know how to do a general shortest path. So, you know, and in this particular problem, it's a tree. Like I said, there's only one unique path. So you could do it with a depth first search, breadth first search, it really doesn't matter. But from that, you construct, you know, I don't know, I'm just writing random number, but on edges, right? So, okay. So the idea that I thought originally was some sort of I should have remembered to look it up, but it's just like some sort of binary lifting, right? Binary lifting related something where maybe we update something, so then we update the binary lifting tree. But I couldn't really figure out easily how to do it, or not that I think it is possible, but it may be very implementationally difficult, right? Challenging, right? So that's why I was like, am I sure? So the way that I thought about it is that, okay, well, for every update, right? I mean, because if you don't know updates, I think this is a straightforward problem. But let's say we update this edge, right? Well, what does that mean? Well, that means that for me, that means that everything in this subtree of 4 will get some delta, right? For some delta, meaning that, okay, if this one goes +3, then everything below it is +3. If this is -3, then same thing, right? Everything under it goes -3. So that's basically the idea that I have this one. And then I go, well, okay. And this is literally my step-by-step thought process. I go, okay, well, let's say we are trying to do that. Then how, you know, how can we update so many nodes quickly? Because if we update one node at a time, that is going to be too slow, right? It's going to be O of n, and you have n squared. I don't even have to look at n, in the sense that if n squared is fast enough, then Leetcode sucks, right? Honestly, so I didn't really look at it too tightly, to be frank. But yeah, right. All right, my hoodie is a little bit weird. So anyway, so then I thought, okay, well, how am I going to update these nodes in a funky way, right? Well, the thing that I thought is, okay, well, actually, we can with a segment tree. I don't know. I know. You already know that I hate segment trees by now, especially as a problem on Leetcode, because it's just not really relevant. It is interesting for competitive, I suppose, but it's just not really relevant. And I don't know. It's just another thing, and I don't know. Is it helpful? But in any case. But then I go, okay, well, because the thing that I like about segment tree for this problem is that you get log n updates, which you kind of need, right? But then I go, okay, well, how do I update, you know, 4, 6, I can't read my handwriting, but all these nodes at the same time with one query, if I had something like a segment tree? Well, then I go, okay, well, if I have a segment tree, then we can just relabel the nodes in a way such that, I think... is it a Cartesian order or Euclidean order? I forget, but I think it's fine to call it an Euclidean order. But it reminds me of, I forget what it reminds me of. It's like it's like a very familiar depth first search thing, but I forget what it's called. Sorry, friends. But in any case, it's about visit order. The DFS visit order, right? And what I mean by that is that, okay, let's say we do a depth first search on this problem, and we have a visit order of, okay, 1, 2. Let me use another color actually. Yeah, we have the number 1, 2, 3, and we go this way, right? And then now we go back up, and then now we go 4, 5, 6, 7, right? 8, and so forth, right? Well, I mean, so forth because it's done now. So actually, I just did everything. But in that case, one property, and I actually did not remember if this was the case. I just thought, okay, maybe I could do something with visit order. I think this is the case, but I had to, it took me I don't know, 20, 30 seconds to kind of verify in my head, which is that given a node, right? Let me change the color again. Given a node, you can just look at, and the reason why we drew these edges is that you can draw the first edge out and then the last edge in, right? And this gives you the node. So for this number 1, whenever we update 1, we want to update, well, we actually include 1, so the 2 doesn't matter that much, but you can say the children of 2, and then the biggest number coming back in, or the last number updated, which in this case is 8, right? So that means that if you update 1 for some reason, or you want to update the subtree of 1, then you just update from, well, 1 to 8, right? And same thing for 4. So 4, this is node 4, right? The 4th node seen, and then the last node return is also 8. So that means that if we update this edge over here, then we just update this subtree, which is node now number 4 to 8. And that's it. I know that I'm not going over segment tree for this problem because I don't know anymore, to be frank. Let me know in the comments what you feel about it, but because I feel like Leetcode has a lot of segment tree problems. Both I don't like it, and also it's just not interesting for me to go over segment tree every time. But the thing that you have to know about segment tree for this problem is just 2 things that you're looking for, right? 1, range update, and in a way such that we can construct 4 to 8 because they're all consecutive, right? So we can do that range update. And then the other is just single index query, or just like a query or fetch, right? So as long as you have those 2, you can write a segment tree for it, and that's it. And that's basically the way that I did it with this one. Yeah, I'm not going to go over the segment tree code too deeply, but I will show it to you here. But again, it requires a lazy seg tree, where you have this update function. Oh, I highlighted wrong. Update function. You have update, divide and conquer, but also the lazy part. Again, I'm not going into this, but yeah, and this is just lazy push. Oh yeah, initial tree build, right? And then the query is the same thing. It's just binary search on the tree, going either the left node or the right node, and then going to the leaf, right? Where L is equal to R, and then you also update the things in a lazy way. And yeah, and of course, both update and query will take log n time, so we don't have to worry about that. Anyway, okay, so yeah, wow, there's a lot more code. But yeah, so that's the segment tree. You can take a look. Honestly, I probably copied this from ChatGPT a long time ago. Like I have a couple of templates that are variation of this, but I think I just copied from ChatGPT a long time ago. So, I could write this. It's not hard, but I just don't find it that interesting, and it's just a lot to write for a problem. But yeah, so let's say you have that, then yeah. So I set up the edge. I like using 0 index, so that's why I kind of subtracted by 1. I add them to the adjacency list. And I also have a lookup, and the reason is just so that, well, you see later, so that when we update, we could see what it was previously in the easiest way. And this is just like the canonical way of doing it, though it's a little bit messy. Maybe I could have done it with just UV and ReU and do both. But anyway, so I have 4 things. It's a little bit awkward, and I think chow none should have been like also just this. But in any case, yeah. So mapping is going to be from. So mapping is the input node number to visit order, right? So this is the thing that we talked about with the visit order of the DFS, right? Parent is just the parent of the node in a rooted tree, rooted from node 1 or 0, depending on how you do it. And then chow out is just yeah, the last node of the children in the visit order, right? So this is basically what gives us the range query that we can do, right? Going from, and then D is just the original distance without any changes, and that's it. And then this is the regular DFS, right? We start from node 1 or 0 because I made it 0 index, no parent, distance of 0. I set up a global current or global to the function. I set up the parent, I set up the mapping because every time we visit a new node, we want to update the current, and yeah. And we set the update the distance, and then this is just child recursion things, pretty straightforward, I hope. And then after we're out, then we just update the child out of the current node to remember that this current is updated with all the depth of searches of the tree and the subtrees and stuff like that. So we just kind of set to current -1. The -1 just because current technically gives you the next number that is used, right? So -1 is the last number that was used. Anyway, so yeah, so that's just depth of search, setting all this up, and then we create a segment tree based on D, right? D being the distance that we have initially. So this is the initial segment tree, and then we have to answer the queries. Queries are also pretty okay, right? If it's type 1, we look at the UVW, again, made them 0 index, and we just look at which one's the parent, right? The idea being that, and they're kind of the same thing, but the idea here is that, for example, if you have, if you're looking through this, okay, maybe that's not a good edge. Let's say you have this edge, right? Then, okay, actually, let's just take this edge. If we take this edge, yellow is terrible. I'm also running out of colors. All right, let's just say gray. Let's say this edge, right? The edge between 4 and 6. Then now it matters which one's the parent, right? Because if 4 is the parent, then you actually want the subtree of 6. And if 6 is the parent, then it would have been the other way around. You want the subtree of 4. So that's basically to get the lower one, so that you do the update. That's what this is doing. Yeah, and basically we get delta. The delta is the change we do because the update function only calculates the delta, and it just sets it to the new value, which is W of the query, and then this is the previous value. We update the lookup for the edges lookup, right, after we set up the delta, and then we just call the segment tree to update the delta. This is the visit order of node U being the child, and child out of that node is kind of the range query that we update, and that's pretty much it. I mean, this is obviously if the other node is the child. Maybe I could render this a little bit cleaner, and that would be fine. Because I guess these two code doesn't actually change, so I guess this could have been outside. And then this you could have just something else. Anyway, whatever, it's close enough. And then else the query, and X is just equal to you could probably run this way. We convert it to the 0 index, and then we look it up the mapping in our visit order, because the visit order is what we put in the seg tree, and then we just do a query on it. Pretty good, pretty straightforward. What's the complexity here, right? This is all linear, just edge lookup things. This is all linear as well, right? Because we look at each node once, we look at each edge once. Though of course in the tree, edge is number of nodes -1, and then we just kind of looked at everything, right? Segment tree, and then for each query, it's going to be log n because we do an update here and query here. So yeah, so the total algorithm is going to be O of n plus q log n, and that's it for time, and O of n plus q for space. Q for space because, well, we just need it for the answer, and that's it. That's what I have for this one. Let me know what you think. Thanks for watching, and yeah, stay good, stay healthy to good mental health. I'll see y'all later. And oh no, sorry, I forgot. I'm tired. You could watch me solve it live during the contest. My computer is like lagging a little bit, so a little bit weird. Hopefully the sound is coming off okay. I don't know if it's just me. Is it okay? Anyway, you could watch me solve it live during the contest now. I'll practice anyway. Alright, Q4, let's go. Shortest path in a weighted tree. What is my leaderboard? That was just like a silly 20-minute penalty. A lot of people got it very quickly, apparently, so people knew what to do. Or I guess I knew what to do. I just kind of didn't optimize it away. All right. Anyway. All right, let's go. Shortest path in a weighted tree. You're given an integer n and an undirected node. Of edges. Okay, I didn't. Okay, you have a tree, undirected weighted tree. You have edges where you reweight. Queries of length q, and where queries of I is either two types of queries: update, weight, and compute the shortest path. Okay. Okay, shortest path from the root to x. From 1 to x, sorry, that's it. Of type 2 from 1 to x. I feel like I mean, this feels like one of those standard problems that I'm like, it's like, whatchamacallit? What's it called? I mean, you create the shortest, oh, it's a tree. So, I mean, it's just, whatchamacallit? The thing with the log n thing, and I guess you do update on that. I'm trying to think because I've never done it before, but I don't think it's that bad. Okay, let's go. Yeah, but I could see how people got it very quickly because I think it's just, well, maybe not that quickly, but it is a standard E problem. It's just I haven't done it in a while. Well, it's not that standard, but it's just like standard enough to be in textbooks, maybe. Okay. And then now we have to make sure that all the updates work, right? If you change the edge, then what happens? Is that true? How many edges do you update on that? So you do. When you do an update, what does that mean? When you do an update, you update all. I mean, that's fine. When you do an update, okay, so a couple of ways to do it, right? So first you get the longest path or shortest path or the regular path. And then when you update, it means that everything that is a subtree of that, right, we do an increment. Can I represent it as a data structure easily? Because basically you want to just go, okay, let's update it for these, like a range update almost. But we could relabel it so that we could do an Orlean tour of the biggest node and then do a range query on the segment tree or something. Is that crazy? How many queries do we have? Yeah, we do a visit order. And then we could just do a range query. So I need a range query subtree. Oh, seg tree, not subtree. Range queries, update seg tree. Yeah, okay, I think that's fine then. Okay. Here's my lazy seg tree. Right, so okay. Okay, let's see, right? So here we go in and out. Yeah, okay, let's go. It's just that first search, right? Because there's a tree, okay. Something like that, right? And that's fine. We get the reset. Yeah. Well, we don't want to set that yet. We want to say visit order, right? So visit order, that's going to be the current. So here we go, okay, mapping of node is equal to current. Right? Well, I guess it's always going to be just current plus 1, but we also have to set the parent. Okay, we'll set the parent. Okay, whatever. That's terrible, Larry. Okay, I think I got this. It may take a while, but I think I got this. We just have to set everything up together. Unless it times out, then it's just that. Okay. So then now we need. Nope. So that means that, yeah, okay. Get an edge. Okay. Okay. Maybe. Just going to keep on using maps for now. Okay, so then we start from, is it node 1 or 0? From 1, -1, 0, right? Okay, print mapping child out parent. Parent's fine. Actually, I mean, this is pretty fine. I thought that looked a little bit weird. Okay, parent node. Oh, because it's one indexed. I hate you, one indexed. Okay. Okay. I mean, that's fine because this is one indexed. Child out means that. Okay. Okay. Nope, this is just confusing. This is P. Okay. Okay. So that means that one should goes from 0 to 3. Okay. Right. Okay. And then now we put everything in the set tree, right? On the distance. Do I not put distance anywhere? Okay, I don't. And I hate one indexed. It makes all my stuff confusing. Let's fix that. I think it's fixed. Okay, so then now, what am I doing again? Oh, seg tree. Nope. Okay, so then now we put on the seg tree. Where's my seg tree? Is that the one where? This is not the one with the initializer. Okay. Okay, and then, okay, now we can enter the queries, which are of 2 types. How do people get it so quickly, other than ChatGPT, I suppose? I mean, it's not, I don't know, I feel like it's very fetchable or doable, but maybe not so quick. Just ignore for now. Else, yeah, query of x minus 1, and then mapping of node. Really? Oh, whoops. I didn't finish typing it because that's what I was confused about. Oh. Alright. I mean, it can be right just because I didn't change anything, but that's okay. I wish there's an easier way for me to compare this to that though, but it looks reasonable. given no updates. Okay, so then now the magic is here. Okay, so UV, which one is the parent, right? So okay, so UV W is equal to K, right? And then okay, so if no, if the parent of U is V, then we want to increase everything under V. So everything including U and all its children, right? So that means that we have mapping of U and then the children out of child out of mapping of U. So we want to change that from okay, so delta is equal to, what was it previously, I suppose, which we have to do, right? Okay, yeah, fine. Okay, right. Okay, so this is the old one. And then the new one is going to be the new W, right? And then we want to sig tree this. And wait. We don't want to update, we want to update with delta. Oh no, that's right, right? That is with delta. Okay, that's fine, maybe. With delta. Else. Wait, is this right? Oh yeah, this is right. Otherwise, then we do the same thing, but it is with mapping of V. Someone like this. Index out of bounds. Why? And it's going to be, this is going -1 to be inclusive. Okay, is this right? I don't think so. 7.4, we have 7.1. Why? So our query changes it from 7 to 4. Alright, there's some printing there. That's good, maybe. I don't know. Negative. Yeah, 7 to 4 is -3. That's fine. So then here we have mapping of 3, child out of mapping of 3. Oh, this is weird. That's why, because we want mapping of x -1. Right? Yeah. That's weird. But I mean, maybe other things anyway, but Okay, so just updates 1 from 7 distance to 4. That should be right? Okay, this one is wrong. What was it before with the update? Before the update, it is a 7. We subtract a delta from it, and it's okay. Well, something's really wrong with the sig tree. I feel like everything else is right though, but my sig tree template is wrong. Seems like update, it is the delta, so why? Update 1 and 1. We wanted to update from 7 to today's not my day. I mean, that's fine. We got it, but we're debugging the segment tree, which is a good sign in the sense that, you know, it means that we're close. Self.size. What does this mean? I've never usually done it before. I usually don't do recursively, so alright, let's look at the recursive version. Maybe that would be more right. Alright, there you go. 7.4. 0427 8325. Okay, so that looks good. So it was sig tree. That's what I get for trying to optimize it by using iterative. Let's give a quick submit. May timeout, but I feel like otherwise everything's okay. Okay, yeah. Not too bad. A little bit slow, but I wonder if there's a clearer way of doing it other than with sig tree. But I mean, because all the reason why I end up using sig tree is because all the ideas that I was thinking of were very similar to sig trees anyway. But yeah. Like, because I want to do the range update, you could probably do some like tree decomposition thing. Oh, they made it so that you can click on these during the virtual contest, which is good. Because in the past I have accidentally misclicked before, but now that my contest is over, it's a little bit less useful, but that's also fine for learning purposes. But can't even load mine. But yeah, all right, I'm gonna call it a night. Thanks for watching, and yeah, thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this contest, these problems, the explanation, everything in between. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye-bye.